So in the previous lecture, we started some of the fundamentals regarding the nanoscience and technology, and we have seen the different dimension levels of one-dimensional scale, two-dimensional scale, and three-dimensional scale. In one-dimensional scale, we have seen how the thin films are fabricated on a substrate. In two-dimensional, we have seen some multi-wall. In two-dimensional scale, we have seen what are carbon nanotubes. And in three-dimensional scale, we have seen some of the organic and inorganic compounds. Okay, so in 3 dimensions, we have seen those. And now today in this lecture, how the nanomaterials, how the materials in nano range, or how the materials, how the fabrication of nanomaterials takes place. Right. So fabrication of nanomaterials, there are different methods so which nanomaterials can be fabricated. Right. So that is what that is what we are going to discuss. Nanomaterials can be fabricated in 2 ways, right? So namely top down and bottom up. So that is what we write: top down and bottom up. Right. So nanomaterials can be fabricated in 2 methods. So that is namely in top down and bottom up. In top-down approach, nanomaterials are constructed. In top-down approach, nanomaterials are constructed by removing the existing material from larger entities. Right. So that is what in top-down approach. When we come from top to down approach, nanomaterials are constructed. Nanomaterials are fabricated by removing the existing material from larger entities. Right. So that is what top-down approach involves: the breaking down of bulk material into nano-sized structures or particles. That is what top-down approach, in the sense we have a bulk material like this. So this is our bulk material. So this bulk material is breakdown into nano-sized clusters like this. So if you see, so this is what we call it as top-down approach. That means a bulk material, breaking down of the bulk material into nano-sized structures or particles is what we call it as top-down approach. So that is what in top-down approach, nanomaterials are constructed by removing existing material from the larger entities. That means a bulk material is synthesized. The bulk material is breakdown or reduced to a nano range, right? So that is what top-down approach involves: the breaking down of the bulk material into nano-sized structures or particles. So this top-down synthesis techniques are extension of those. Top-down synthesis are extensions of those that have been used for producing micron-sized particles. Right. So this top-down synthesis, the synthesis of nanomaterial for nanoparticles, synthesization of nanoparticle from top down, from top bulk material to nano range, from bulk range to nano range. So that means the top-down synthesis. These techniques are extension of those that have been used for producing micron-sized particles. That means the micron-sized particles. Right. So this is one of the method of fabrication of nanomaterials. That is what top-down approach. So in bottom-up approach, we have materials and devices are built atom by atom, or molecule by molecule, or by cluster by cluster. Right. So atom by atom. In bottom-up approach, materials and devices are built by atom or molecule by molecule by molecule, or by clusters to clusters, by cluster to clusters. So this is what we call it as the bottom-up approach. The bottom-up approach, in bottom-up approach, materials and devices are built up by atom or molecule by molecule. That means in top to bottom, we are breaking down the particle from large entity to a small entity. That means to nano range entity. In bottom up approach, what we are doing, we are taking from bottom, that means small to nano. So in which the range can be fabricated. So that is what we call it as fabrication of nanomaterials. That's what I told you. Nanomaterials can be fabricated in two ways, namely the top-down approach and bottom-up approach. In top-down approach, see, this top-down approach and bottom approach is what the fabrication of nanomaterials. But there are different techniques for the fabrication of nanostructures also. Right, so we'll see what are those different techniques. What are the different techniques in which nanostructures can be fabricated. Right, so this is what we speak about the nanomaterials. That means synthesizing of nanomaterials. That is what we are writing. In top-down approach, nanomaterials are constructed by removing existing material from the larger entities. That means top-down approach involves the breaking down of the bulk material into nano-sized structures or particles. So in top-down synthesis techniques are extension of those that have been used for producing micron-sized particles. So the particle size should be very micron, in the range of micron-sized particles. In bottom-up approach, materials and devices are built atom by atom, or molecule by molecule, or by cluster by cluster. So this is what we speak about, some of the fundamentals regarding the fabrication of nanomaterials in top-down and bottom-up approach. So if you go for this, the synthesize, we can see here in this block diagram, in this structure, we can see this is a synthesis of nanomaterials. So nanomaterials can be synthesized by top-down approach, top-down process, or by bottom-up process. So this bottom-up process can be fabricated. The bottom-up process can be fabricated by different techniques, different fabrication techniques, right? So the bottom-up process can be fabricated by different fabrication techniques like electrodeposition, right? So electrodeposition and solution phase reduction, sol gel method, solution gel method. That is what we call sol gel method and colloidal method. So these are the techniques, or these are the fabrication methods in which these include in the bottom-up process. So we shall see what is electrodeposition, what is solution phase reduction, sol gel method, colloidal method in the next coming video lectures, right? So we shall see what is electrodeposition, what is solution phase reduction, what is sol gel method, and what are colloidal methods. Of course, these all methods come under the bottom-up process, bottom-to-up process. Whereas in top-down process, where we are seeing the synthesis of material can be fabricated by two processes. One is a top-down process and is a bottom-up process, where we have seen bottom-up process, in case of bottom-up process, the process that include in bottom-up process electrodeposition method, solution phase reduction method, sol gel method, colloidal method. So these are the different methods which comes under the category of bottom-up process. Now, if you go for top-down process, so top-down process in the sense taking a large entity, taking a bulk material to reduce into the nano-sized material, right? So they're taking a bulk material, taking a large material and making that material to a nano-sized material. That means breaking down of the bulk material, If you take a sugar lump, that is a bulk material. If you break that material, if you start give some, if you apply some pressure on that material gets breakdown, right? So we get what in the for the large quantity of sugar sample or sugar lump, we can get the particles of sugar. That is what sugar particles we get. Right. So these sugar particles are nothing but of nano size, and the sugar lump is what we call it as a bulk size. So this process is what we call it as top-down process. In top-down process, the methods that we use, are nothing but the ball milling method, plasma arcing method, and laser sputtering, and other is the vapor deposition method. Right. So these are the various methods that we use in top-down process. What is that? What is a ball milling method? So we'll discuss each and every method from our top-down process, bottom-up process. We'll discuss each and every method in coming our videos lectures, in coming future video lectures, right? So in top-down process, we have the ball milling method and plasma arcing in the sense arc of plasma will be generated. And that is the laser sputtering. Laser sputtering is nothing but deposition of solid material on a liquid phase. right? The deposition of solid material, right? So that is what sputtering. Sputtering will include, we'll see that laser sputtering. And other is a vapor deposition method. That is what vapor particles vapor particles of the solid material, of the metal, vapor particles of the metal will be get deposited by some vapor. That is what we call as vapor deposition method. So this vapor deposition methods can be of two types. One is the physical vapor deposition method and other is the chemical vapor deposition method. So we'll see that in detail in the coming future lectures. So if you go to the synthesis of nanomaterials, and the fabrication of nanomaterials includes two processes. One is a top-down process and other is a bottom-up process, right? So in top-down process, we have the ball milling process, plasma arcing, laser sputtering, and vapor deposition method. Whereas in bottom-up process, we have electrodeposition technique, right? So we'll see that what is electrodeposition technique and what is solution phase reduction. What is solution phase reduction? How the solution phase reduction method can be used as a bottom-up process, and what is sol gel method? That is the solution general method. So sol gel method and other new method that is called the colloidal method. So we shall see. So what are these different methods that in which nanomaterials can be fabricated for synthesis of the nanomaterials, right? If you go to the top-down process, if we discuss the top-down process in detail, under this process of fabrication, that's as I told you, bulk materials are broken into nano-sized particles. Bulk size material. That is what we have seen. This is our bulk material. This is our bulk material. This is our bulk material. So these bulk materials are broken into first taken into powder form and then goes for the nanoparticle size. That is what under this process of fabrication, bulk materials are broken into nano-sized particles, right? So in this approach, there is no control over the size and the morphology of the particles. In this size, so we have in this approach, there is no control over the size and morphology of the particles, right? So that is what, this is your bulk material. This bulk material when broken, that means if that is what we use some ball milling method. If you apply some ball milling method on a bulk material, that will show as a powder, and this powder when reduced to nano range, that means if they are further if they are further given under the ball milling, then we can get appearance of the nanoparticles of this different range. That is what is a bulk material. So this is a powder material and this is the nanoparticles in the nano range, right? So some common methods of top-down method are as follows, as we have seen in our previous flow chart. So there are some common methods of top-down methods are as follows. One is a ball milling method, as we have seen. There is a plasma arcing, laser sputtering, and vapor deposition methods. So these are the different methods where this top-down method can be employed. So this is a ball milling method, plasma arcing, laser sputtering, vapor deposition method. So this is what one of the top-down process. So if you go to the bottom-up process approach refers to the building of a material from the bottom, that is by atom, a molecule by molecule, or cluster by cluster. So that is what we told you when we speak about the bottom-up process. So the bottom-up process includes the electrodeposition, as you have seen in our previous slides. This bottom-up process includes electrodeposition, solution phase reduction methods, sol gel methods, and colloidal methods, right? So that is what bottom up refers to the building up of a material from the bottom in the sense by atom, right? Atoms, and after atom, molecule by molecule, and by clusters. So that is what colloidal dispersion is a good example. Colloidal dispersion is a good example. Colloidal dispersion is a good example of bottom-up approach in the synthesis of nanoparticles. So when we speak about the synthesis of nanoparticles, colloidal dispersion is a good example. Colloidal dispersion is a good example of bottom-up approach in the synthesis of nanomaterials. So there are different methods for the synthesis, as you have seen in our previous as I have seen in the previous slide. So there are different methods of bottom-up process. One is the sol gel method that you have seen. There's a colloidal method, electrodeposition method, and solution phase reductions and solution phase reduction. So these are the general different methods used for synthesis of nanoparticles in bottom-up process. So the most important feature of this process, is that size and morphology of fabricated nanomaterial will be well controlled. Right, the size and the morphology, the size of the nanoparticle and the morphology. Morphology means smoothness, right? The size. The most important feature of this process is that the most important feature of this bottom up process is that the size of the nanoparticle and morphology. Morphology is smoothness of fabricated nanoparticles are well controlled. That means that the controlling of morphology and size can be limited in bottom-up process. That is what we see here. We have certain atoms. These atoms form clusters. From these clusters, we get the nanoparticles. So these are the atoms. These are the atoms. Atoms forms to clusters and clusters to nanoparticles. That is what the most important feature of this process is that size and morphology, size of the nanoparticle and morphology, smoothness of the fabricated nanoparticles, or the size and morphology of the nanoparticles can be controlled, right? So control, this is one of the biggest advantage of this bottom up process, right? So this is what we regarding the bottom up process, right? So we shall see some of the properties, some of the fundamental facts where we can establish some certain relations, right? Right. Bottom-up or self-assembly of approaches to nanofabrication use chemical or physical process operating at nanoscale to assemble some basic units into larger structures. As component size decreases in nanofabrication, bottom-up approach provides an increasingly important complement to top-down techniques. So inspiration for bottom-up approaches come from biological systems where nature has harnessed chemical forces to create essentially all the structures needed by life. Researchers hope to replicate nature's ability to produce some clusters of specific atoms which can then self-assemble into more elaborate structures. For example, liquid phase techniques can be based on inverse mixers globules and floating on a non-aqueous solution in which their polar or hydrofluoric invert into the form of molecule. So that is what these were some of the applications, some of the techniques where we can go for the top, bottom, and bottom up approach. Now, if you go for an example of assembly that achieves a limited degree of control, an example of self-assembly that achieves a limited degree of control over both formation and organization is the growth of quantum dots. That is what we have seen in our previous lectures, right? So Indium gallium arsenides can be formed by growing a thin layers of indium gallium arsenide, right, on gallium arsenide in such a manner that repulsive forces caused by a compressive strain in the gallium arsenide layer structures, the formation of isolated quantum dots. After the growth of multiple layer pairs, a fairly uniform spacing of the dots can be achieved. Another example of self-assembly of an intricate structure is the formation of carbon nanotube under the right set of chemical and temperature conditions. So this is what we can see, the difference that we observe in microelectronics and nanotechnology. So if you see here, so this is what the microtechnology, which is at the range of 0.1 to 1 to 10 micrometers, whereas in bottom-up approach self-assembly, we can observe the range of nanoparticles ranging from 1 to 100 nanometers. Where the microelectronics, the top-down approach building space is around 0.1 to 1 micrometer, whereas in nanotechnology bottom-up approach self-assembly is around 1 to 100 nanometers. So this is what we can bring the difference between the microtechnology and the nanotechnology, right? So that is what we can bring some of the fundamental facts between the microelectronics and nanotechnology, right? So if you see this slide, the cup, here you can see the cup was probably created in Rome during the 4th century, right, CE, and shows a different color changing the light from opaque green to bright red. bright red. This is the most famous example of this so-called dichroic glass, which is called an optical glass, right? Actually, it represents some tiny amount of nano-sized gold and silver that gives these unusual optical properties. That is, gives, you see, unusual optical property. This happens because at the nanoscale range, the electron cloud located on the surface of a gold nanoparticle has the possibility to resonate with different wavelengths. It's possible to resonate with the different wavelengths of light depending upon their frequency and amplitude. So this phenomena is now well understood and reproduced even at the laboratory demonstrative level. That's what we are telling. This cup, if you see here, this cup which in which it was kept in the British Museum in London, right? So one is of the reflected light, another is by transmitted light. If you see here, so this figure A represents the reflected light, and this is what the transmitted light. When light is transmitted in this direction in the nanoscale, right? So we get the color of the color can be changed. So that's what this cup was probably created in Rome during the 4th century, right? The 4th century CE and shows a different color, changing the light from opaque green to bright red. Opaque green, this is what opaque green, and it is changing its color to bright red. So this is the most famous example of this so-called dichroic glass. So dichroic glass is one of the optical glasses, right? Actually, it represents some tiny amount of nano-sized gold. Actually, it represents some tiny amount of nano-sized gold and silver that gives these unusual optical properties. That give the nano-sized gold and silver that gives these unusual optical properties. So this happens because at the nanoscale range. This happens because at the nanoscale range, the electron cloud that is located on the surface of the gold nanoparticle has the possibility to resonate with different wavelengths of light depending upon the frequency and amplitude, right? So this phenomena is well understood. If we see this particular level at the laboratory, when we see this same mechanism in the laboratory also, we can that is what it can be observed, produced even at laboratory demonstrative level. We can observe, we can see that. So this happens because at the nanoscale range. That's what we are telling. The nanoscale range. That is what the importance of nanotechnology. So this happens because at the nanoscale range, the electron cloud located on the surface of the gold nanoparticles, as the gold nanoparticles has the possibility to resonate for different wavelengths at different frequencies, right, depending upon their own frequencies, right? So this phenomena is well understood and reproduced even at laboratory demonstrative level, right? So if you nanomaterials, these are some of the nanomaterials. These nanomaterials have unique characteristics, right? So these nanomaterials have unique characteristics. So if you see some of the properties and examples, what are the properties and how these nanomaterials have properties, and what are the properties that can be mapped for properties that are mapped for some examples, right? So that is what nanomaterials have unique characteristics. One of the properties of nanomaterials have catalytic properties. They have electrical properties of nanomaterials. They have some magnetic properties which show a supermagnetic behavior, superparamagnetic behavior, and ferromagnetic behavior, superparamagnetic behavior, and at all magnetic nanostructures. Magnetic nanostructures can also be fabricated when we study about the properties of magnetism, right? And we have some mechanical properties of nanomaterials, right? And we have the optical property. We have the optical property of nanomaterials, and we have spherical properties, right? So spherical property is also one of the important properties of nanomaterials, and of course, a very important properties are biomaterials or bio-nanomaterials. That is, the materials, the properties related to biological methods, right? So if you see the examples related to each and every property, so if you see for the catalytic property, so the examples for the better examples for the catalytic properties are the efficiency of catalytic efficiency through higher sulfurs are better. They have better catalytic efficiency through higher surface to volume ratio, right? The catalytic efficiency is higher in surface to volume ratio. If you see the electrical properties, increased electrical conductivity in ceramic based materials and magnetic nanocomposites, and or nano composite materials or nanoporous materials or magnetic nano composite. Increased electrical resistance in materials, right? Electrical resistance in metals. That is what the electrical properties, that means increased electrical conductivity. Electrical conductivity in ceramics can be increased. And magnetic nanocomposites, that means we have the combination of different compositions of magnetic materials. That means electrical conductivity in ceramics and magnetic conductivity or magnetic property in nanocomposites can be increased, right? And not only that, the electrical resistance in metals can also be increased. The electrical resistance can also be increased in the sense we have certain scattering parameters. We have certain scattering parameters for different electrical properties. That means the scattering parameters, that means how the electrons are being scattered, right? So that is what increased electrical resistance in materials. So the electrical resistance, that means the specific resistance of metal can be increased when we speak about the electrical property. If you come to the magnetic property, we have increased magnetic coercivity up to critical grain size, right? So increased magnetic coercivity in the sense, see, we have the MH loop, in case of magnetic property, we have the MH loop, right? So this MH loop is what we can sell. So this is what the hysteresis loop. So this is what the hysteresis loop. So this is what loop. So this is what we call it as the coercivity. Just a minute. So this area, this is what we call it, that is retentivity, and this form is what we call as a coercivity. So coercivity is nothing but the demagnetizing field. So this is our MH field, MH loop. So this loop is the demagnetizing loop. This MH field, that is which depends upon the coercivity, that is what increased magnetic coercivity up to critical grain size. So when we study the magnetic property of nanomaterials, that means that due to the grain size, due to the grain size, the magnetic coercivity increases. When there is an increased magnetic coercivity up to the critical grain size, then that particular nanomaterial in magnetic material show the behavior of superparamagnetic nature. That is what we call it a superparamagnetic behavior. That is what increased magnetic coercivity. So the magnetic coercivity increasing to the grain size, increasing up to critical grain size, shows the behavior of superparamagnetic nature, right? So this superparamagnetic nature, that means it is nothing but a single domain size. It's a single domains, right? So single domain size, when we study about the magnetic property, it shows a single domain property. That's what increased magnetic coercivity up to a critical grain size shows the property of superparamagnetic nature. Right. So this is one of the important part. We cannot tell this is important. Every property of nanomaterials are very important to study the application oriented, right? So that's what. If you come to the mechanical property, so if you see the mechanical property, we have improved hardness and toughness of the metals and alloys, ductility and super plasticity of ceramics, right? So the mechanical property, if you take a metal and if you start touching it, due to its ductility, it immediately comes into the powder stage. It comes to the powder stage. If you take a metal, if you take an iron or mica, if you just press it, the mechanical property, that is what improved hardness and toughness of metals and alloys, ductility and super plasticity of ceramics. Right. So this is one of the essential properties. This is also one of the essential property to understand the hardness and toughness of metals and alloys. Alloys is nothing but a combination of different metals, right? And to study the behavior of malleability and ductility and the super plasticity of ceramics. That means we need to study certain material like ceramic material, right? Metals, alloys, and ductilities. To study the mechanical strength, we need to study about the mechanical properties of nanomaterials, right? So if you come to the optical properties of nanomaterials, so that means there is a spectral shift of optical absorption. And fluorescence properties. Spectral shift of optical absorption and fluorescence particles and fluorescence properties, increased quantum efficiency of semiconductor crystals. So spectral shift of optical absorption spectral shift of optical absorption and fluorescence properties increased quantum efficiency of semiconductor crystals. So it is one of the property that comes under the optical property. That means there is spectral shift. That means the spectrum in the electromagnetic spectrum, if you see, the fluorescence property increased the quantum efficiency of semiconductor crystal. And if you come to the next property, that is spherical property, so it increased selectivity hollow spheres for specific drug up transportation and controlled release. So increased selectivity hollow spheres for specific drug sterlical and surgical devices, right? So that is what we can increase selectivity hollow spheres for specific drug transportation and controlled release, right? So if you come to another property, the biological property, where we have increased permeability through biological barriers. So these biological barriers can be membranes or blood-brain barriers, etc. So they improve biocompatibility. They improve the biocompatibility. So that is what it comes under the biological method. So these are the different properties where nanomaterials are unique characteristics. So out of these very important characteristics of magnetic properties, right? So where we can find, we can see the nature that where we can see, we can find the super paramagnetic behavior. By controlling the thickness, by controlling the grain size, by controlling the critical grain size, right? If you increase the coercivity of the critical grain size, then it shows a super paramagnetic behavior, which is a single domain state. So nano optical properties, that is scale changes to nanomaterial. The scale changes of materials come with changes in color. That is scattering plus absorption is nothing but extension, right? When light is incident on a nanoparticle, it can be scattered or absorbed. When light is incident on a nanoparticle, it can be scattered or absorbed. The fraction of light that is scattered or absorbed can vary greatly depending upon the particle diameter. Right? When a light is incident on a nanoparticle, it can be scattered or absorbed, right? So the fraction of light that is scattered or absorbed can vary greatly depending upon the particle diameter. At diameter less than 20 nanometers, nearly all the extension is due to absorption. Right? So when the particle size is less than 20 nanometer, nearly all the extension is due to absorption. At a D greater than 100 nanometers, at the diameter greater than 100 nanometers, the extension is mostly due to scattering. The extension is mostly due to scattering of the nanoparticles. Right? So by designing a particle with a larger or smaller diameter, the optimal amount of scattering, and absorption can be achieved. By designing a particle with a larger or smaller diameter, the optimal amount of scattering and absorption can be achieved. Another relationship between size and absorption or scattering is that aggregation can increase the effective size of a nanoparticle. Resulting in an increase in scattering. This is why 20 nanometer diameter silica particles are clear in solution, but resuspension of dried 20 nanometer silica particles aggregated will be milky or white in color. Right? That is what by designing. So that is what the scattering plus absorption gives the extension. That is scattering and the combination of scattering particles or absorption gives the extension. When light is incident on a nanoparticle, it can be scattered or absorbed. The fraction of light that is scattered or absorbed can vary greatly depending upon the particle diameter. At diameter less than 20 nanometer, nearly all the extension is due to scattering. At diameter greater than 100 nanometer, the extension is mostly due to scattering. By designing the particle with a larger or smaller diameter, the optimal amount of scattering and absorption can be achieved. That means we have to design a particle where we have the larger or smaller diameter, where the optical amount of scattering can be achieved. That means the controlling of scattering parameter can be achieved. Controlling of scattering and absorption should be achieved. So that is what, by designing a particle with a larger or smaller diameter, the optimal amount of scattering and absorption can be achieved. Another relationship between size and absorption or scattering is that aggregation increases the effective size of a nanoparticle, resulting in increasing scattering. So this is why we use 20 nanometer diameter silica particles are clear in solution, but resuspension of dried 20 nanometer silica particles will be milky white color. So if you see the tools and technology, if you see for the tools and technology, there are several important modern methods. That is what we study. When we study about the bottom up process, we have seen that the size and the morphology can be controlled. So the size and morphology can be controlled by the morphology, the smoothness of the particle. So smoothness of the particle can be controlled by using certain tools, right? So the tools and technology, there are very several important modern developments. So we'll see what there are several important modern developments. That is, first one is the AFM, that is what atomic force microscopy, and other is the STM, that is scanning tunneling microscopy. So scanning tunneling microscopy is the first fundamental microscopy which was invented to design a nanoparticle, to see the structure of a nanoparticle. So see the nanoparticle. That means as soon as so scanning tunneling microscopy are the scanning probes that launched nanotechnology. That is what we are writing. The scanning tunneling microscopy, STM, are the scanning probes that launched nanotechnology. So other is the atomic force microscopy, which we can see the surface morphology and surface morphology. So there are various methods of fabrication of nanomaterials. Not only the synthesis of nanomaterials like top-bottom or bottom-up approach, there are other methods which nanostructures can be fabricated. So that is what various techniques of nanolithography, such as optical lithography, that is what photolithography we call it as, optical lithography or photolithography, or other we call it as X-ray lithography, and other is dye pen nanolithography, and other is the electron beam lithography, that is what E-beam lithography we call it as. This E-beam lithography can also be called as inkjet printer. So these were all developed. These are the tools where nanotechnology have been implemented, right? Nanotechnology have been implemented to see the morphology, to see the size, and to see the fabricators, see the structure is fabricated. So these are the various tools, right? So one is optical lithography. Optical lithography is also called as a photolithography or UV lithography, we call it as. Another is X-ray lithography, another is a dip pen lithography. We'll see all this, what are these different tools in detail in the coming video lectures, right? So other is the electron beam lithography. Electron beam lithography is nothing but E-beam lithography, where we can write that particular. If you want to make a design on a substrate, if you let you take a substrate as silicon substrate, right? You take silicon substrate like this, and if you want to write on the silicon substrate, we need different lithographic techniques. So one of the lithographic techniques we need is photolithography, technique, and other is the E-beam lithography technique. Right? So E-beam and lithography. So E-beam lithography, when you want to write on this particular silicon wafer, first we need to write it. That means the design. That means if you want to make a nanostructure on the silicon wafer, that particular lithography, E-beam lithography, will write on this particular lithography with certain nanometers, nanometers, and whatever the dimensions you give to the particular, to write on that particular silicon wafer, right? So that particular lithography, either that is E-beam lithography or X-ray, photolithography, can be used to write a pattern. If you want to pattern on the silicon wafer, that means etching is to be done on the silicon wafer to certain nanometers. So for that etching process, electron beam lithography or photolithography is widely used. Right. So lithography in MEMS context is typically the transfer of pattern. That is what I told you. Transfer of pattern into a photosensitive material by selective exposure to radiation source such as light. Right. So lithography is a MEMS. That means microelectronic microstructure context is typically the transfer of a pattern into a photosensitive material by selective exposure to a radiation source such as light. If you see here, if you can see this figure, So I'll tell you this figure in the next coming video, right? So that is what lithography is a in MEMS devices, lithography plays a vital role. That means writing a pattern on a silicon wafer, or etching a silicon wafer to certain nanometer is not possible by normal lithography methods. It is not possible by any fabrication technique. So only the fabrication method which we need to etch a silicon wafer to few nanometers is only by the process of lithography only. This lithography are of two types. This lithography can be either photolithography or by using electron beam lithography. So this electron beam lithography and these lithographic techniques where nanostructures or nano etching of nanostructures in MEM devices can be achieved at IIT Bombay or at a Nano Research Fabrication at Center for Nanoscience and Engineering at IISc Bangalore. Right. So these are the two institutes where we can find the etching of where we can find the patterning, where we can write certain patterning. Patterning is that we can pattern a circular, we can pattern a triangle, we can pattern a rhombus, we can pattern a rectangle, we can pattern a circle. So whatever the patterning, so lithography is the best method to pattern. That is what lithography in MEMS context is typically the transfer of pattern into a photosensitive material by selective absorption, by selective exposure to radiation source such as light. Right. So these are the certain applications. That is what nanoboards close to the scale of 10 power minus 9, largely in the R&D phase. Nanoboards of 1.5 nanometers across, capable of counting specific molecules in chemical samples. These nanorobots would be microscopic in size. It would probably be necessary for very large numbers of them to work together to perform the microscopic and macroscopic tasks. Capable of replication using environmental resources. So the applications are detection of toxic components in environment, in drug delivery, and we have in biomedical instrumentation. So what are the approaches in nanotechnology? As we have seen, we'll come to what are the approaches in nanotechnology. Approaches in nanotechnology bottom up. In the bottom up approach, different materials and devices are constructed from the molecular component of their own. They chemically resemble themselves by recognizing the molecule of their own breed. So that is what examples of molecular self-assembly are Watson-Crick base pairing and Watson-Crick base pairings. This is what we call it a Watson pairing, and other is the nanolithographic method. So in the top-down approach, nano objects and materials are created by larger entities without bouncing its atomic reactions. Usually top-down approach is practiced less as compared to bottom-up approach. So solid-state techniques can also be used to create devices known as nano electromechanical systems or NEMS. That is what MEMS is. MEMS is a electro system, and where here we use NEMS, that is nano electromechanical systems or NEMS, which are related to micro electromechanical systems or MEMS. MEMS became practical once they could be fabricated using modified semiconductor device fabrication technique, normally used to make electronics. So the materials used for this NEMS or MEMS are zinc oxide, that is dirt repellent, hydrophobic, cosmetic and stain resistant. Another silver ion, that is which is having a helium property. Another aluminum silicate, that is scratch resistance. Another gold ion, that is gold ion for chip fabrication and drug delivery techniques. So if you come to the applications of nanotechnology, we have lot of applications for nanotechnology. So that is what innovative applications. These innovative applications in nanotechnology can be energy, drugs and medicine, nanotechnology, nano devices, optical engineering, defense security, bioengineering, cosmetics, and nano fabrics. Where that means these are some of the applications of nanotechnology. Right. So we have all these applications, that is energy related applications, medical and drugs related applications, nanobiotechnology, nano devices, optical engineering, defense and security reasons, defense for defense purposes, bioengineering, cosmetics, and nano fabrics. So these are the certain applications where nanotechnology can be imparted. So nanotechnology in drugs and cancer provides new options for drugs, delivery drugs and drug therapies, enable drugs to be delivered to precisely the right location in the body and release drug doses on the pre-identified schedule for optical treatment, attach a drug to nano-sized carrier. they become localized at the disease site, that is cancer tumor. They can then they release medicine that kills the tumor. Current treatment is through radiotherapy or chemotherapy, and nanobots can clear the blockage in arteries. So these are some of the applications where nanotechnology in drugs and cancers can be used. So nanotechnology in fabrics, right? The properties of familiar materials are being changed by manufacturers who are adding nano-sized components to conventional materials to improve performances. For example, some clothing manufacturers are making water and stain repellent clothing using nano-sized whiskers in the fabric that cause water to build up on the surface. In manufacturing bulletproof jackets, making spill and dirt resistant antimicrobial and antibacterial fabrics. So these are the some of the applications of nanotechnology fabrics, and we have nanotechnology in mobiles, right? So nanotechnology in mobiles we have, right, and nanotechnology in electronics, and nanotechnology in computers, and we have certain features, right? So we shall see what are the nanotechnology in mobile and what are nanotechnology in electronics and the next previous slides. Right. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.